So we have spent our time now deriving how electromagnetic waves propagate, and we have understood the properties like power flow, like polarization. We have related them to material properties and how waves can attenuate with distance. But in order for radio waves to be interesting, we have to have them interact with something else, with some material, some object. For example, in order for an antenna to receive a radio wave, the radio wave has to strike an antenna. That antenna could well be, for example, a metal wire. And when the electric field strikes this metal wire, it's going to induce currents to flow along that wire, and that's what we can sense with some electronics. So that's one way in which a radio wave can interact with some object in order to produce a response. Another example is, for example, a radar, where we fling a radio wave towards something like an airplane or a bird or a rain cloud, and we expect the radio wave to reflect off of any objects that have a different electrical property and reflect and come back to the source. So again, radio waves are only interesting once they interact with something in the environment. And so we're going to spend a couple lectures here discussing the ways in which radio waves can reflect off of boundaries. And we're going to start out with reflection off of a perfect conductor. So let me just take a minute to remind you about what happens to sinusoidal signals on a transmission line, since that will be sort of a good starting point, right? And let's just consider when we have a sinusoidal steady state wave propagating on a transmission line with Z0 as the intrinsic impedance of that transmission line. And we're going to consider the case where we have a short circuit on the load, just a direct electrical connection, which basically means that there is 0 voltage at the end of the line. So what we did was we described the input wave, right? We're assuming that we're injecting some voltage here, the input. And let's take this point right here to be Z equals 0, with Z increasing in that direction, in which case the input wave is going to be described as follows. The voltage as a function of Z equals some constant V0 times e to the minus j beta z, right? This reflects or describes a positive propagating wave that has amplitude V0, and its phase is changing as a function of distance because of how the wave takes a certain amount of time. So if you move forward in the positive z direction, that's a reduction in the phase because there's a delay. The wave gets there later. And this parameter beta was called the wave number. It was 2 pi divided by the wavelength lambda, or it's equal to omega divided by the propagation velocity. All right, so this was the input. And we also know that the reflected wave, which we're going to call output here, and let's describe that as the output voltage after the reflection, will be equal to V out as a function of Z equals V0 times e to the positive j beta z. And I'm going to put a negative sign right here to account for the reflection coefficient at the load, which equals -1. Right, that's the reflection coefficient right there. Right, or gamma L is -1. I'm just going to remind you that these are actually phasors, so I'm going to put a little phasor squiggly line over the V in, over the V out, and even over the V0 positive negative. All right, so now we've got our input and output waves at before and after reflection. And the total wave, therefore, is just going to be the sum of the input and the output. Which works out to be V0 times e to the minus j beta z minus e to the positive j beta z. This part right here, an e to the minus j beta z plus e to the positive j beta z, you can actually describe that a little differently. This is a -2 times V0 times j times the sine of beta z. So this describes what we call a standing wave pattern, which is to say that at the load point at z equals 0, we have to have a voltage that's 0. But that's not necessarily true everywhere else. It's possible that we might have voltage in other locations. So remember, this is a phasor right here, right? This total is a phasor. So let's look at this. The amplitude of this is going to vary with distance, but the phase of that is always the same. There's only a real component to this. There's only an imaginary component to this. There's no real component. So the phase is going to be constant as a function of distance. And so if we plot this phasor as a function of distance, we're going to see something that looks like this. It's going to start out at 0, and it's going to increase, and then it's going to hit this 0 point right here, and it's going to decrease, and we're going to have this repeating. This is a sine wave. This point right here is the half wavelength point, and this point right there is the quarter wavelength point. Now what I've drawn is actually the envelope, and so what's really happening is that the sine wave is going to be oscillating back and forth with this amplitude. The amplitude that you see in red is the amplitude that the sine wave is going to be oscillating. So anywhere you go, you're going to see an oscillation, but the amplitude of that oscillation will simply vary depending on your location. So if you're located at this point right here, at the half wavelength point, sorry, that is lambda over 4 up there. It's the quarter wavelength point. If you're located right here at the half wavelength point, you will see no voltage at all. What actually happens is that the input voltage and the output voltage are perfectly canceling each other out, and so you're left with nothing. Whereas at the quarter wave point, the input voltage and the output voltage actually add up constructively, and so you actually get twice the amount of voltage. And this level right here, that's half of that peak, that level is V0. You can see the same on the negative side. This is negative V0, right? The input voltage that you're putting into this system. And this is what we call a standing wave. It's not moving in any way, but it clearly is oscillating in some way to reflect the fact that there are waves that are propagating. All right. You can see this again with WinTLS. I encourage you to look back at some of the older lectures for this. What we're now going to do is we're going to analogize this perfectly to a situation where we have a radio wave that is propagating and striking a perfectly conducting boundary. So here's our boundary, and on this side we have a perfect electrical conductor. What that basically means is that the electrical conductivity sigma is infinity. Right? And let's define our axes the same way we did before. We're going to call this the z equals 0 point. And we're going to have positive z being to the right or into the conductor. And z equals 0 is right at that boundary. All right. On this side, we're going to say we have some kind of a dielectric, or let's just call it air. Right. And this is basically this perfect conductor, which is something like a metal. Now let's consider that we have a radio wave that is coming in and preparing to strike this boundary. And the electric field of this radio wave is pointed in this direction. So this is the electric field. I'm going to put a I there to indicate that it's the incident electric field. And let's say that this wave is propagating directly at this perfect conductor at a 90-degree angle. That's the only case we're going to consider here. We're not going to consider when it comes in at an oblique angle. That will be covered in later courses, but we're just going to stop here. So this is what we call the K vector, the vector that points in the direction of propagation. And I'm going to put a little subscript I to indicate that it is, again, the incident K vector. Now remember, the electric field cross the magnetic field has to equal the direction of propagation. So from this, we can automatically figure out that the magnetic field will be coming out of the page. And so we're going to call that HI, incident. So that's the incident wave. Now our assumption is that there could well be a reflected wave. And let's just take a leap of faith. We can prove this later, but let's take a leap of faith that the reflected wave is also going to be coming straight backwards from the perfect conductor. So we'll call this K vector, but I'm going to put a subscript R for reflected. This reflected wave will have an electric field pointed in this direction. And this will be E sub R. And it will also have a magnetic field that's pointed in this direction, H sub R. So what we like to do is figure out, how does ER and HR relate to EI and HI? Can we derive one from the other? The only constraint that we have to work with is something about our boundary condition. That at the boundary, we're going to have a constraint of how the electric field and magnetic field must result. Much like in the transmission line, we had a constraint that at the load, we had to have a zero electric field. And that is basically how we could figure out what the output voltage is. We're going to do the same thing for electric field and magnetic field. And so let's write out the equations for what electric field and magnetic field are. All right, so the electric field, we're going to write this as E0I, and that's going to be a phasor, times E to the minus J beta Z. And let's just pick a direction and say that this direction upwards along the boundary is the X direction. All right, in which case we're going to have the electric field pointed in the X direction. Right, so we have a linear polarized wave. We can just sort of, to make it simple, align our axes such that the X direction is in the direction of the electric field. And this minus J beta Z tells us that the wave is propagating in the positive Z direction. All right, so that's the incident wave. The reflected wave will look like this. It's going to be E0R for reflected times E to the minus J beta Z. And let's assume that that is also in the X direction. All right. So from this, we can now ask the question, well, can we determine the way E0I and E0R relate to each other from boundary conditions? And the simplest boundary conditions is that the electric field at Z equals 0 must be equal to 0. That is the definition of a perfect conductor. There is no electric field. And so this basically pops out directly from that, and that's what we're going to call our boundary condition. So what that means is that the electric field I at Z equals 0 as a vector, plus the electric field of the reflected wave at Z equals 0 must add up to be 0. All right, if we just apply that to our definition of electric field and incident and reflected, from that we can pretty quickly figure out that E0 for the incident wave must equal negative E0 of the reflected wave. Right, that basically we can take this and replace it with an I right there and add a negative sign. That's what boundary conditions will do to this problem. Now we're going to define something called the reflection coefficient. And the reflection coefficient, not surprisingly, will be the ratio of the reflected electric field to the incident electric field as phasors. And this works out to be -1. Now this should hopefully look familiar because that was also the reflection coefficient for this case, where we have a wave reflecting off a short circuit for which the reflection coefficient is -1. Right, so we're imposing a condition where there is no voltage at a load, and that implies a reflection coefficient of -1. Here, we have a perfect conductor, which means no electric field, and from that, we get a reflection coefficient of -1. So electric field is going to be very analogous to voltage when we consider this as to be kind of like a transmission line with a short-circuited load. All right, now let's take a look at the magnetic field then. All right, so let me slide this aside. Given that we know this about the electric field, the magnetic field is always going to be the same as the electric field, except we have to divide it by eta, number one, and we have to orient the direction such that E cross H equals the direction of propagation. So let's do those two things and write down what the magnetic field is. Oops. All right, so let's start out with what incident magnetic field is. I'm just going to take the electric field, E0I, and I'm first going to divide it by eta. Remember, eta is the intrinsic impedance of the air, or the impedance of the propagation medium, which is square root of mu divided by epsilon. Right? It's just a constant for whatever material is on the other side of the boundary from the perfect conductor. And now we're going to write an e to the minus j beta z, since it's propagating in the positive direction. Now let's think about the direction here. We need to have E cross H equal to the positive z direction, since this is propagating in positive z. So this has to be located or pointed in the y direction. All right, so that is the reflected wave. Sorry, that's the incident magnetic field. Now let's take a look at the reflected electric field. Right, and I'm again going to take this negative E0I. I'm going to take the amplitude of this signal for the incident electric field, and I'm going to divide it by eta. And we're going to take E to the minus j beta z. And we need to make sure that E cross H again equals now the negative z direction. And so this works out to be in the y direction. All right, but we need to put in another minus sign here to account for the fact that it's now propagating in the negative z direction. So we have to have y hat cross negative, negative y, x hat cross negative y is equal to negative z. And that's what we need. So this is going to be a negative y right here. These two negatives are going to cancel out. So I'm just going to get rid of them. Right, one of those negative signs was to account for the fact that E cross H has to equal the direction of propagation. The other negative sign was simply taking this electric field and dividing it by eta. So let's cancel those two out. This will become a positive. And now we've determined what our magnetic field is, both for the incident and the electric field and the reflected magnetic field. Now notice for the magnetic field, the reflection coefficient is different. It's actually positive 1. Gamma is positive 1 for the magnetic field H. And this is identical to what we talked about with transmission lines, where the reflection coefficient for the current was always a negative of what it is for the voltage. And that is also the case when we talk about fields reflecting off of objects, except where we're just replacing voltage with electric field and we're replacing current with magnetic field. But everything else is basically the same. And if we take a look at the wave that results, we're also going to get a standing wave, which is here's our boundary. We're going to get the electric field, which has to be 0 at the boundary. And basically the phasor for that electric field will have an amplitude that oscillates sinusoidally and a phase that's constant with distance. So this is the phasor at any given moment. The electric field is basically going to oscillate up and down to plus or minus whatever that value is. Right here, it's going to be a big oscillation. Here, it's going to be a small sine wave. Here, it's going to be non-existent. All right, the magnetic field will be a little bit different. And let me just draw that side by side here. Magnetic field will be a little bit different because that reflection coefficient is positive 1. And so at the load, we actually get a doubling of the magnetic field. So the magnetic field will look like this. It's going to start out very high, and it's going to crash down to 0. And then it's going to proceed like this and continue on. So this point lines up here. This is 1/4 wavelength away from the boundary. And this point right here is 1/2 wavelength away from the boundary. And this represents the magnetic field phasor. All right. So the magnetic field operates the same way that the current does as a standing wave from a short-circuited load, right? And this is basically how radio waves are going to reflect off of conductors. And this is very useful since there are many instances in which radio waves are going to interact with conductors, like an antenna, which is a perfect conductor made of, or something close to a perfect conductor that's metallic. A radar reflecting off of an airplane. An airplane is mostly made out of metal. That's a very good conductor. So this will more or less describe how a radio wave interacts with a flat surface that is metal when the radio wave comes out at an angle. Now, things are a little bit different when the radio wave comes in at an angle like this. We're not going to cover the details, but long story short, the radio wave is going to reflect at an equal angle from however it comes in, but it will reflect pretty perfectly, and boundary conditions will still be satisfied in that case. Right. Now, one thing I want to point out is, well, in order for this boundary condition to exist, we have to satisfy all of Maxwell's equations. And this is actually going to give us a little bit of insight into how the wave reflects. You might ask, why would the wave bother to reflect? Why can't it just keep going on? So let's take a look for a second, because boundary conditions are also going to tell us something about what the magnetic field is, right? Now, the perfect conductor dictates that the electric field has to be zero inside it, but it actually has nothing to do with the magnetic field. There's no reason why you can't have magnetic field inside a perfect conductor. But we do have a boundary condition, which is that n hat cross h1 minus h2 equals js. All right. Now here, we are going to make the assumption that since there is no wave propagating into the metal, and the electric field is zero, that must imply that the magnetic field is zero. So let's just define this for a second. And I'm going to call this material 1, and we're going to call this material 2. So the metal is material 1, in which case the n hat vector, by definition, points into material 1, in which case h1 equals 0. All right, so we've got n hat cross negative h2 equals js, the surface current. We now know what H2 is, because H2 is simply going to be the sum of the incident magnetic field with the reflected magnetic field. So we sum all these up. The incident plus the reflected will equal to what we're calling H2. All right. And this works out to be the following. H2 equals 2 times E0I as a phasor divided by eta. This is evaluated at z equals 0, right? So this is the value of H2, and it is oriented in the y direction. In this case, n hat equals positive z hat. So if we take z hat and cross it with 2 E0I divided by eta in the y direction, what you get is a non-zero surface current that looks like this. All right, so Js, the surface current, is oriented in the x direction, that's z hat cross y, and it has a magnitude of twice the incident electric field divided by eta. All right, so let's take a look at this and put it into context. Right, now, first of all, this is oriented in the x direction. The x direction is located along the boundary, as indicated here by these charts. Now, first of all, notice that the surface currents are pointed in the same direction as the electric field. That should make sense, because the electric field is basically going to drive currents in the direction from J equals sigma E. That's Ohm's law. So even though sigma is infinite, we still have the concept that as soon as we apply an electric field, we have to be establishing some current across this conducting body. So it certainly makes sense that the surface currents are in the same direction as the electric field. All right, but let me think a little, let me go a little more deeper than that, because what we're learning here is basically the way in which these reflections happen. That what's going to happen is that this electric field strikes the boundary. The boundary will then have surface currents that are induced along that. And those surface currents will then basically emanate a wave in both directions. The wave that goes to the left is going to add up to the wave that comes in. That's going to construct the reflected wave. The wave that goes to the right into the metal will be perfectly destructively interfering with the wave that's coming across. So the way to think of it is, here we got a perfect conducting boundary. We've got a wave coming in. And in essence, you can think of the wave as continuing on. It just keeps going. That's our incident wave. But the incident wave also induces surface currents right here. And those surface currents are going to launch a wave in two different directions. It's going to launch a wave right here. I'm going to draw this carefully. And it's going to launch a wave in the other direction. That may look like this. Now, to the right of the boundary, the red and the blue are going to perfectly kill each other. And therefore, you have no electric field and no wave in the perfect conductor. But to the left of the boundary, because you have the waves propagating in different directions, they don't cancel each other out. Everywhere, they only cancel each other in certain locations. And that's what we call a standing wave. So the way in which waves reflect is that you have basically an interaction with the boundary. You have surface currents that are set up on the boundary, and those surface currents basically re-radiate a new electric field. It acts like a new source that turns around and sends wave backwards. All right, so that basically concludes the way in which waves reflect off of perfect conductors. In the next lecture, we're going to take this one step further, and we're going to consider waves that reflect off of dielectrics or non-conductors, and we're going to have to add one more piece to the puzzle.